Recording is rolling. It is Thursday, January 9. Of course, I wasn't in school yesterday, had jury duty, so got a little story for you guys, brought my jury summon so you guys can see a little bit about how the process works. Uh, I do have your guys' puzzles printed out. Here's for my honors classes, and here's for my conceptual classes. It's both chapter 8, coincidentally, is rotational. Whoops, sorry, no, this is my AP. Oops. Sorry, this one right here. Here's my honors. Here we go. Honors, conceptual, and then just showed AP accidentally. It turns out they're all chapter 8, just different books. Okay? So I'll get those to you guys later so you guys can see what questions come up about rotational dynamics. Maybe some rotational inertia, probably a good amount of torque, maybe a little bit of angular momentum. Okay? But I don't have a due date for those yet, but probably a couple weeks from now about. Okay, that's AP stuff there. Okay, so here's really what we're doing today. Got a few slides and notes for you guys with just these purple banner slides, right? Focusing on mostly torque, a little bit of rotational inertia. Got see, right? Got a video demo for you guys. And then I put in your hands this lab page just at the very beginning of class before I hit record. Okay? So this is a torque lab. It's going to be over 2 days. It's really two halves. So on one side is a seesaw looking side, and on the other side is a scaffold looking side. I have also purple banner posters for those. So I'll show you guys what those are about. But it's going to be today and tomorrow. Going to be some labs going on. All right. So before we get to the physics stuff, how does all this jury stuff work? Because you might get a jury summons yourself one day. So I got this in the mail about a month ago. It says show up at the courthouse January 8th at 8 a.m., which is yesterday, which I did. Right, so before I went there, I had to fill out a survey. The survey was a few questions, but mostly they were looking for things like, is there anything that would possibly disqualify you as a juror? And there's a list of options down here. And also there was a compensation. So since the way the system works, they just pull people out of society. Everybody's missing their jobs. How do you get paid for your job? Now, since I work for the school board just goes ahead and pays teachers that are missing for jury service, right? A lot of jobs will do that. If you have a salary position, it'll probably do that. But say you're working at McDonald's or something, right? They're probably not going to pay you for working on a jury. So turns out that the compensation for working on a jury, stay right here, it's $15 per day. Right. Now, for me, I don't have to worry about that myself. Get it from the school board. But if you had like a minimum wage job, then you only get $15 a day working on a jury. Okay. So I did yesterday. I showed up 8 a.m. Checked in, whole day. I went to a big room. There were a bunch, like dozens of potential jurors sitting there. Now, kind of how the system works, we didn't actually get to this point, but there's a part called jury selection. So you might start out with dozens of potential jurors, and then the prosecutor and defense will each select, well, they try to narrow it down to like 12 jurors ultimately, right? But there might be reasons where they don't want this or that juror. For example, if you're a defense attorney, maybe you want a jury pool that looks a lot more like who could possibly empathize more with your own client, right? Like if maybe like a similar age and demographic, or they have a similar job or similar story where who can empathize more with my client. They try to eliminate jurors that would be the opposite of that, right? So there's the whole process. Now, we never got to that part of the process because a plea deal was taken at the last minute. So this was a few hours in. So I was sitting there for a few hours. But here, part of the process was they called at some point, is there any reason that anybody would not be qualified or could leave if they wanted to? And they have a list of reasons here. So what's going to, let's see, I got mandatory disqualifications would be if you're not a citizen, if you're not a resident of the county, if you're under prosecution, or if you're a convicted felon, rights not restored. Here's a list where you could leave if you wanted to. So things like if you're a law enforcement officer, because there could be possibly a conflict of interest, expectant mother, if you've given birth in the last 6 months, if you have extreme hardship, if you've served already on a jury in the last 12 months, if you're 70 years or older. So if you're like 73 years old, you could go up to the judge and ask to be dismissed, and they would go ahead and let you go. Right? And there's a few other ones, but those are the main things we're looking for. Right? So right, if you're like heavily pregnant or have some hardship or something like that, or you're really old, right? Which I was none of those things. So I sat there for a few hours. Now, I think it's something like 90% of people who are in prisons never actually go through a trial, which it's your right to go through a trial. If you're ever accused of anything, you can definitely choose that option, right? But again, I think the number is close to 90%, and then plea deals. So I think that's what happened yesterday. I have no idea who the defendant was or what the allegations were. I don't know any of that. What I do know is after a few hours, they said that a plea deal was taken. So I think how this works is that the police sit across from the defendant, probably with an attorney. If you're ever in this position, never talk to the police without an attorney, right? Uh, and they present all the evidence, like, okay, here's all the evidence we have against you, and this is exactly what the jury's going to see. And if you go ahead with the trial and you lose, which we think you will because we're prosecuting you, then maybe, for example, you might get like 5 years in prison or something. But if you take this plea deal, maybe we'll knock that down to like 2 or 3 years and probation, which is a lot of your sentence, right? Trying to save everybody some time. So something like that happened. All right. So if you guys ever get a jury summons, you know a little bit more about that process. All right. So right here, let's pull up these notes right here. Notes time. All right. Oh, we go back. So I'm going to rewind way back. I know a lot of these slides you guys saw yesterday. I'm going to do a real fast recap and then kind of hone in on the ones today. So you guys remember turntables from last semester? You guys remember these kinematic formulas in a rotational sense? You guys remember these graphs that go with, say, a turntable so to stop, the graphs look like that. Okay. Center of mass is just a weighted average of mass. So you can add up mass times location, add them all up, divide by the sum of mass, that gives you the average location called center of mass. Have an activity for that too, so in time eventually. Okay. You guys remember a definition of what makes something stable or unstable? Showed you guys a couple days ago. Did you guys try this with your phone? You guys try to flip your phone like this? Okay. It's like strangely difficult to do. That's just kind of fun food for thought. Okay. All right. Now, these 2 meter sticks I passed around class the other day, and if you just pick them up, they feel like the same mass, same weight, everything. But if you rotate them back and forth, all right, now the one in the right picture on the right, where the masses are slide further out, has more inertia in a rotational sense. Call it more rotational inertia. The physics formula for that is mr squared for a single point. And if it's multiple points, you just add them up, hence sum of mr squared. Okay? If you have here's some common like rigid bodies that could rotate. Like, how about this basketball here? If you spin this basketball on your finger, take some torque to get it to spin. How much torque to spin it, how fast, depends on rotational inertia of the basketball. Okay? Now, you could divide the basketball into a billion different points and say mr squared plus mr squared plus mr squared for every single point relative to this central rotating axis. Okay? But the aggregate effect for a spherical shell, like a sphere where all the mass is at the surface, ends up being a factor of 2/3 of mr squared. So you say, now you can prove that with calculus. I'm not going to prove that in class, but I want you guys to kind of say, okay, kind of see where this sort of come from. Okay. All right. Parallel axis theorem. So go back to this table. These table values only work relative to the axes that are shown on, you guys see like all these dashed line axes, right? And for the basketball, it goes like straight through the center, right? Like if you're spinning the basketball on your fingertip, then 2/3 mr squared works perfectly fine. But if the basketball is, say, rolling across the floor or revolving around an axis that's parallel to its own central axis, that's parallel axis theorem, you have to add the md squared in. Right, that's all. It's not too bad, right? So rolling across the floor, you guys notice rolling across the floor, it's not actually rotating about its own center. It's actually rotating about this point down here. So it's the 2/3 mr squared off the table plus another mr squared because it's rolling across the floor. Like if you got it rolling, right? Across the floor. All right. The lab paper in front of you guys right now is a torque lab. So does everybody look up here? Everybody paying attention up here? Okay. So focus right here. If I'm turning a nut with a wrench or opening a door about the door hinges, it's this radial arm, R, crossed with this force, F. Okay. Now, when I say cross with, that's a multiplication, but I'm only multiplying the perpendicular components. Okay. So guys, if you were pressing straight into or away from the wrench, like straight toward, like parallel to the wrench arm, would this ever turn at all? No, right? So you have to push some component that's perpendicular. In fact, if you want to maximize the torque, say like this is rusted over and it's really hard to turn, you want to maximize your torque. You want to press exactly perpendicular to that wrench arm. Okay? So if you're given this angle theta, the R times F times sine of that angle theta. Okay? Now watch for this though. I forget if this comes up in your textbook puzzles or not, but maybe in college in the future. Okay? Sometimes you might get a curveball version of this. Because what if they don't give you this angle theta that I show up here on this slide? What if instead you get the angle relative to the perpendicular? You guys see my mouse cursor is tracing out this little tiny angle right here? Let's call that alpha, right? And if they gave you that angle, or you could solve for theta first, do 90 degrees minus that. Right? Let's call this alpha, right? If you play directly off alpha though, this would no longer be RF sine. It would now be what? RF cosine, right? So RF cosine of alpha, right? So RF sine of theta as shown, or if I have this angle alpha, it'd be cosine. Okay. Right. So careful with that. All right. Now that's where torque comes from. It comes from R cross F. Right. What it results in is an angular acceleration. You guys see this alpha angular acceleration? That's if you have a net torque. So I have this applied torque here, because I'm pushing on the wrench at the end, right? Maybe I subtract off the torque at the point of the nut. Maybe it's like rusted over or there's some friction. I subtract that out, and we'll get a net torque. That's going to cause an angular acceleration. How much angular acceleration? Depends on the net torque. Also depends on this I. Now, what could this I be? Well, I can get that if I just go back a couple of slides. You guys get this one right here? Rod about the end. You guys see that? Does that look a lot like a wrench trying to turn a nut? I think it sure does. I bet that could be a really good approximation right there. If you know the mass of the wrench and you know the length of the wrench, the 1/3 ml squared, that's a pretty good approximation for what could feed into this I right here. Okay? Tell you how much the wrench accelerates angularly. Okay? All right. So there's your torque. Okay? All right. Now, guys, on that slide, guys, everybody look here. Look here. Am I trying to turn that? Does that look like clockwise or counterclockwise? Counterclockwise. Yeah, like opposite of the hand motion on the clock, right? Counterclockwise, right? Unless you're standing on the other side. Because what if you're standing behind the screen looking like towards you? Now it would change, wouldn't it? So whether it's going clockwise or counterclockwise really depends on where you're standing in the room. Okay? Now in this class, we're just going to stick to clockwise, counterclockwise. That's also true for my AP classes. They just stick to that convention. Okay? But since it depends on where you're standing in the room, there's mathematically a better way to talk about torque, which is this right-hand rule, right? Right, now, this is a little bit beyond the scope of this class. We probably won't do this in this class, but I want you to at least have seen this and be a little bit familiar with it. So if R is represented by the direction of my index finger, and I go 90 degrees to that with my middle finger, F, there's the direction of the force, okay? Instead of saying on this XY plane down here, clockwise or counterclockwise, I can define torque along a Z-axis, like a third axis, okay? And that is the same regardless of where you're standing in the room. So everybody's perspective can be the same. Okay. So you have to open up a third dimension. Okay. Okay. And now you can solve more complex cross products. Right. See, show hands. Show hands. Guys, how many guys have seen a cross product in a determinant that looks like that? You guys ever seen that? A matrix and a determinant? Okay, so that's what, two of you guys? Only two? Two, maybe? Right? All right. So if you've seen this, awesome. Maybe algebra 2, possibly. Yeah, algebra 2. Okay, that's where I saw this. Well, this is where I first saw this. Here's what we do. I remember I did do this in my college physics class. We did solve some cross products with this matrix method with a determinant. Also, where matrices pop up here, I'll tell you another application of this too. With these determinants and matrices is for when I was in grad school, I did economics. And economics, suppose you got a bunch of economics variables, you could treat each one as its own dimension. Okay? So say like maybe we want to introduce this policy, how's it going to affect the economy? Well, what variables are at play? See, we got this unemployment rate and this interest rate and this inflation rate and this Gini coefficient rate. You put this all together, maybe each one could be its own dimension. You might have like 10 different dimensions. You might have like a 10 by 10 matrix or something crazy like that. Right? And how do you solve that? Now, how do you solve that? Okay. Again, I don't think we'll do this in class, but this is maybe a good skill to know, especially if you're going in the hard math and science route in college. Oh, I've got this video from a YouTube channel called Organic Chemistry Tutor. You guys see Organic Chemistry Tutor? Is this playing? Okay. Where he's going to solve a cross product. Now, I've got this guy muted just so I can narrate it myself. First, he's going to define his two vectors. He's got them as A and B. You guys see this right here? Now, what this means is if there's a vector, it's 3 in the x direction, 5 in the y direction, and -7 in the z direction. That's what I, j, and k are. They're x, y, and z axes. Okay? He's got another vector he's going to cross it with. Let's see, 2 in the x, -6 in the y, and 4 in the z. Now, how that kind of aligns with my picture. You guys see I got this wrench at this crazy orientation in 3D space? I got I, j, and k axes. That's like x, y, and z axes. Okay? It's some crazy 3D orientation. Like this much in the x, this much in the y, and this much in the z. Okay? Also, I could apply a force. That's also some crazy 3D direction. Okay? And that's going to cause some crazy torque about this nut that's right at the origin point. Okay? Okay. So instead of A and B, you can call this R and F for R cross F, because we're about to take a cross product of R and F right here. Right? Oh, A cross B, let's call it R cross F. I sets up what's called a matrix, and I showed sort of how to solve that on that poster, but and two of you guys I think know how to solve these. Right? Right? Some of you guys might see these in college, and I just want to introduce this idea right now. Okay? Really, the best way to learn this is just be handed a bunch of these puzzles and just to solve a bunch of them. Okay? But you guys are seeing right now how he's solving this. Right? So he's setting up some matrix math, solving this determinant. He shows exactly how to do it. And you got to fast forward through all this. Right? And at the end, he's going to get, there it is. There it is. He just got the answer right there. See where he says C equals? Oh, hey, guys, what does that arrow above the C represent? It means it's a what kind of value? Vector value, right? Which in this case could represent torque. He's calling it vector C. I might call it the torque, right? So A cross B was like R cross F. Oh, wait, this right here. Torque is R cross F. Torque is a vector. Force is a vector. Radial arm could be a vector, has an orientation. Okay. So this is the answer. Actually, he could stop the video right here because he just solved it. Right? Now that's the torque along a single axis. So the actual motion of the rotation could be along a 2D plane that's perpendicular to that. Right? Thinking like right-hand roll version. Okay. But the rest of this video, he does a check. So I want you guys to see the concept of the check he's going to do for the rest of this video. Okay. And it goes like this. Guys, if two vectors are perpendicular to each other, then how much of those two vectors are parallel? Nothing at all, like zero, right? So what he's about to do is what's called a dot product to see, well, how much are parallel, right? And he's just trying to draw that out here. But the torque is going to be necessarily perpendicular to each of the radial arm and the force, right? So now R and F might be or maybe not, right? But the torque definitely has to be. So is A dot C equal to 0? That's like radius dot with a torque. Because if it is, then he can say that he didn't make any mathematical mistakes, that he for sure got this correct. So he's just doing a little check here, make sure this, in fact, zeroes out because it should. It should zero out. Let's see if it does. Oh, yeah, and it zeroes out right there, which means that he didn't make any math mistakes. So he got the correct answer to start with, right? Which was, okay, rewind back to about the 4-minute mark. It's right about the 4-minute mark. Which is right there. Bam. The actual answer could be this right. Okay? You guys can see that? All right. So that's there. You might see that someday. And then going back to this class, we're going to tend to stick to clockwise, counterclockwise. Okay. All right. This lab we'll save for another day coming up. All right. This is the last slide I showed you a couple days ago, equilibrium. So remind you guys how this works because this is what you're going to use today. Okay. So last semester, I said the forces sum to 0 along each axis if you like sum to 0, right? But starting this week, we're going to also bring in the condition the torque also has to sum to 0. If you go into engineering, say civil engineering, you want to build a big static structure, that's definitely going to be equilibrium. This is the starting point for every single thing you're ever going to design. Say, okay, I know everything has to go to equilibrium. I need, if I'm working in 3D, that's the 6 conditions on the right side. And in 2D, it's these 3 conditions, right? Like that. Okay. All right. So these 2 slides right here, this is the front half of your lab page, and this is the back half of your lab page. We're going to do the seesaw today, and we're going to do the scaffold tomorrow. Okay. All right. So do you guys see the seesaw? Like if you had 2 friends on a seesaw trying to balance it out? Okay, this is what we'll do today. I'll walk you guys through an example, and then you'll have the rest of the class to do this yourselves. You'll hold on to this page at the end of class because tomorrow we'll do the scaffold. Right. Talk a little bit about scaffold, just to plant this idea so you can sleep on it tonight and come back tomorrow and it's just a little better, okay? You guys remember Paul Hewitt, right? Show all those Paul Hewitt videos, right? So his story is he got out of high school. He didn't know what he wanted to do with his life. He spent many years of his life just working odd jobs. He was a boxer at one point. People punched him in the face. And he got this job painting signs. And he was up on the scaffold just like painting a billboard. He was walking back and forth on the scaffold. And he started, hey, I wonder, as I walk towards the right side, how does that change the tension in these ropes? These tension, the left tension, the right tension. Right? And this was one of these questions that got him thinking, that got him interested in physics. Then I think he didn't go to college until he was like 26 years old, and got a physics degree, and eventually wrote that blue book that's in the back of my room there. Right? So, and of course made all these videos that you guys get to see. Right? So see if you guys can figure this out. Guys, if you're walking on the scaffold, left to right, I'm walking towards the right. What do you think is happening to the tension in the right side? Is it increasing? At the same time, what's happening to the tension on the left side? Decreasing. Do you think those 2 tensions, the sum of them, always stays the same? Yeah, in fact, it has to hold up all the weight, doesn't it? The scaffold plus whoever's walking on it, right? But what is each individual tension? You cannot solve that with force alone, which is last semester. Last semester, you could, maybe if you're standing right at the center, you could say, well, it splits half and half. I think I gave you that question last semester. But if you're not standing at the center, you can't know what each individual tension is unless you also bring in torque. Otherwise, you don't have enough equations. Okay, so you can only solve this with torque. That's tomorrow's adventure. Okay, well, let's go back to the seesaw though. Okay, so here's what we're doing today. So I'm saying the sum of the torque goes to 0. Okay, so if I get this all balanced, now in place of this triangle pivot point, I'm going to just hold it with a spring scale, and that matches the picture on your lab page. You guys see that? There's a spring scale. Hold on, right at the 50 centimeter mark is where we'll put it, just to keep it real nice and fundamental. Okay. All right. So I'm making the claim here. Oh, if I have, say, some mass, some weight on the left side, so I've got mg weight at some distance 3x, can that create 3x crossed with mg is 3x mg worth of counterclockwise torque on the left side? Counterclockwise is usually considered positive, so we'll call it that. Okay. Okay. Then if I want to zero out the torque, well, I need a clockwise torque. So I got 3 times the weight at a third of the distance. Oh, look at that. X times 3 mg. That zeroes out with 3x times mg. You guys see it all zeroes out? You see that? I don't know if you guys remember, but I did actually use this last semester very briefly. Do you guys remember that poppers lab? You guys had those poppers and they pop straight up, figure out what's the kinetic energy? The only way to solve that was you had to know the mass of the popper. And what I did was I set down a ruler and a known lab weight on one side and I put a popper on the other side, I think a couple of poppers, okay, like that. Okay, and then you balance it out and you can solve for the unknown weight, okay? Which is exactly the premise of today's lab. Okay. So where's my lab paper? I had one ready to go. Well, here it is. Okay. Got this ready right here, right here. Okay. So are you guys on the side that just has the single spring scale pulling up? Okay. Not on the side here. If I flip this over, okay. Not on the scaffold looking side with the 2. That's tomorrow. Let me flip over to today. Okay. So here's today with the 1 spring scale pulling up. Is that? Okay. Okay. So remember the principle of how this is going to work is that if this is all balanced out, the torque needs to zero out. And the goal you're headed towards, see where it says mystery lab weight? Right? You're going to put on 2 lab weights. Say I got 1 here and 1 here. Right? You guys got a box of lab weights in front of you. Right? And you're going to obviously know what they are because you've been working with these all year long. Right? But we're going to say, what if you don't know what the one on the right is? And you're allowed to know what the one on the left is, but not the one on the right. Okay? And you're going to calculate it going through this torque process. And at the very end, you guys see this very box that says F. F as in force, as in a weight, right? Right. And when you calculate this number, you can go back and see how close is it. For example, maybe they did the calculations and got like 4.8 newtons. And say, oh yeah, that's really close to 5 newtons. But I did a pretty good job. Okay, you see that? All right. Now, let's start with the one on the right side of the page. The one on the left side is the exact same setup, but it's a perspective change. One of these is maybe a little more intuitive than the other way to do it. Okay, so I'll walk you guys through some examples, right, and then I'll have you guys do this yourselves with your teammates for the rest of class. Okay? So the one on the right side, you guys see this note here that says pivot point scale? You guys see that? It says pivot point scale right there, right? So I'm going to treat the point of the scale, which I'm going to park right at the 50 centimeter mark, as the pivot point, which I think is the most intuitive point to do from anyway. Right? I left it up to you guys. You probably pick that point anyway, right? But later on, that'll change. So hold on to that idea because that'll change later. But I'm not gonna do that. Right. So I'm just focused on this right side of the paper. Okay. Right. And mystery lab weight. Right. Do you guys see over here? It says F right is a mystery. You guys see F right is a mystery. Right. So let's say you don't know what that is. You're going to calculate it and compare it. Right. 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 So relative to this pivot point right at the center, it's 50 centimeter mark. Do you think that this left weight right here is causing a counterclockwise torque? Right, so I'll call it torque left. Okay. And this mystery weight on the right, is it causing an exactly opposite torque right, to provide equilibrium? Okay, equilibrium. Right. Right. So I have kind of a setup here. See if I can flip this to the centimeter side, sort of. Right. Right. Take a couple of weights. Right. Now, I'm going to put my spring scale right at the 50 centimeter mark. So I got this right at the 50. Okay. Take, let's say a big weight, put it kind of over here. Boink. And take a small weight and put it over here. And I want to pick this whole thing up and try to balance this out. Now, I'm going to get these kind of close to the pivot point because I'm trying to sort of fit this in this camera screen. but it's a real small space, so it's kind of hard to, come on here, kind of hard to get this here. All right. It shows up on camera, but I got to scoot these around because that is definitely not balanced. So I have to scoot these around until it actually does balance. Oops. Okay, actually, right there, it's pretty dang close to balance. Okay, so let's see what values I'm working with here. Okay, so of course I got the spring scale at the 50. Okay. My left weight is, I have this mark right here. Now, my left weight I'm allowed to know. Guys, the 1 kilogram mass weighs how many newtons? 10 newtons. Great. Now, don't copy this down because I want you guys to do your own, or unless you happen to have the same weight. But I'm going to put 10 newtons myself because that's my weight right there. Okay. You see the next box says F left minus X scale, X left minus X scale. That's this distance. It's falling apart here. Okay. I'm trying to show it here. That's this distance right here. And I know I had this at the, well, right. Guys, what's 50 minus 37? Is that 13? 13? Okay. And I'm calling it negative because I'm calling it on the left side. So F left minus F scale. So anything minus 50. It's really 37 minus 50, isn't it? Okay. So for me, it's negative 13. Again, don't copy that down because I want you guys to do your own, but I'm just giving you guys an example. Okay. Therefore, is that negative 130 Newton centimeters of torque? So we got newtons and centimeters today. Okay. Now, the weight of the meter stick could be causing a torque because it has some weight also. Okay. But relative to its own center, it's always going to zero out. That's why I zeroed these boxes out. Okay. I'll give you the weight of the meter stick. Actually, this number right here, you can copy. Let's call it 1.2 newtons. I measured a bunch of them this morning. They were all kind of in that ballpark. That might not be 100% accurate, but it's probably pretty close to. I bet your meter stick with all the little browns on it, it's probably close to 1.2 newtons. Okay. Okay. Plus or minus a little bit. Okay. Now the scale. When I would read the scale was reading pretty close to 16 newtons, plus or minus about a newton. So I'm going to say 16. Now, you guys don't write that down. You guys write down whatever number is on your scale. But F scale, for me, it was 16, and negative because it was pulling up versus the weights are pulling down. That's opposite directions. Okay, you guys got all that? Okay. Now, I have, well, let me record one more number. I'm going to assemble this back together. Let's see, get this as close as I can, because the last number I need is where was the location of this other weight to balance it out. I didn't quite get that. It's really close to right there. Looks like okay, it's at the 78 mark. Guys, what's 78 minus 50? 28. So that's an arm of 28. You guys see that? Right. That's gonna go, you see all the way down to the bottom. Right. Again, don't write that down. I want you guys to figure out yourself with your own setup, but with my numbers, it'd be like that. Okay. Okay, guys, good. Right. Say where all these are coming from. Okay. But this is one of those labs that, like, if you know the big picture of how torque works, like if you follow that seesaw off the poster, then I really try to make this really fundamental and like, okay, we're trying to clicks and understands. But if you don't know the principle and you're just like looking at all the little boxes, like, it's a lot of boxes all over the place. Right? Okay. But if you understand the big picture, then everything kind of clicks in place, right? So there's 4 potential torques. There's the torque of the left weight, there's the torque of the right weight, the meter stick itself has some weight, possible torque, and the spring scale is providing a weight and possible torque. But 2 of those zero out anyway, because the weight of the meter stick, I'll treat it as own center mass at the 50 mark, and the spring scale is also at the 50 mark. That's why these 2 numbers are 0. So what's all the torque I have so far is just this box right here. And for me, that's negative 130 Newton centimeters, right? Right. But guys, for balance, if the whole thing is balanced, then what's the sum of all the torque equal to? 0. If that's true, then how much torque was provided by the very last weight? It's the opposite of this number here, so it zeroes out. So for me, if it was negative 130 here, this one must be positive 130. Okay, again, different for you because you're going to bring up your own. Okay, and I know its location, like the radial arm, the location from the center. So let's do what's 130 divided by 28. that works it up to be 4.6 something newtons, which is really close to its actual weight, which is 5 newtons. Do you guys see that? Right, this is actually 5 newtons. I knew that all along, really, but if I make a believe, or if I didn't know, I did the calculation. Look, it looks like it's 4.6. That's pretty close, isn't it? Pretty good? Pretty good? All right. All right. Any questions so far? Questions so far? Do you guys think you could break that up and figure out the radial arms and do the torque? Right. All right. Now, the left side of this paper could be the exact same physical setup. You don't actually have to change anything about the meter stick or the weights. Leave everything exactly there. In fact, you're looking for the same premise, same question. What's the mystery weight on the right side? What you are changing is your perspective. Do you guys see this note right here I just circled? It says pivot point 0 centimeter mark right there. You see that? What you're going to do is change your perspective, and I'm going to call the far end of the meter stick the 0 centimeter mark as my pivot point, okay? Which is a completely random point. And the principle I'm trying to show you guys is that you don't actually have to pick any particular point as the pivot point. Like maybe the most intuitive point is the point of the spring scale, right? Which can have some advantages too. Like if you couldn't read the spring scale, then the torque from the spring scale would zero out anyway, which is what we just did, which can be kind of nice to solve textbook puzzles, right? But in principle, you could pick any point in the universe and the torque still zeroes out. And I want you guys to see that that'll be the case, and that'll still let you solve for the same force, right? Right, so what do I call this? This was that. Now, relative to this point, my left weight, which was 10 newtons, was at the 37 centimeter mark. Right, so there's my 370 Newton centimeters. Right? The weight of the meter stick was 1.2 newtons times 50 centimeters from the point is 60 Newton centimeters. The spring scale itself was reading about 16 newtons. Now it's negative because it's pulling up, but 16 times 50, 800, and it's negative. Right? So here, just go ahead and finish this off just to show you guys my version. And of course, you guys are not going to copy my numbers. Right? You're going to make up your own. This is negative 370 Newton centimeters of torque so far. Therefore, this mystery weight must, relative to this pivot point, must be providing positive 370 Newton centimeters to zero everything out. That was sitting at the, I forget what it was. Was it, I think it was the 78 mark, wasn't it? 78, right? Now, relative to the 0 mark, that is 78 centimeters. Right? So going for the finish here, I hope this is, again, pretty close to 5 newtons. Let's see if it is. What's 370 Newton centimeters divided by 78 centimeters? 4.7 newtons. Look at that. Look at that. Right? So the actual weight's 5 newtons. The method I started with on the right side of the page gave me 4.6. That's really close to 5. So I'm happy with that. And this new method I did, I picked this completely arbitrary point at the 0 centimeter mark. That's like, why would anybody ever pick that as a pivot point? It's not intuitive at all. But mathematically, it gives you the same correct answer. They said 4.7 newtons, pretty close to 5, right? All right. So I'm going to close up the recording right there. You guys got, a solid 20 minutes. That's perfect to do this lab, help each other out. I'll walk around, help you guys out too. And then tomorrow we'll do the scaffold side.